All right, I'm gonna get started before you guys make me laugh too much. All right, so today we're talking about 10.1, which is the law of sines. All right, and with this we do move into the final section of the class, chapter 10, some various applications of trig. We're going to talk about law of sines, law of cosines. These two things can be used to solve any triangle, not just right triangles. We're going to talk a bit about polar coordinates, a bit about complex numbers. Trig with complex numbers is always going to be fun. And I'm pretty sure there's other stuff we're doing in this chapter too, but those are the big ones. All right. So we're going to do a little example 0 to show that really you don't need this section at all to solve any problem. Yes, I'm telling you, you don't need the section, but the section will make it easier and a lot quicker. Okay, so let's see what we get. Solve for x. All right. Say we have a triangle right here. It's not a right triangle. This is a small 15-degree angle. This is a 35-degree angle. Let's say this side is 10. Later on, by the way, we will call this an angle side triangle, an AAS triangle, because we have one angle, then its adjacent angle, and then an adjacent side after that, AAS. Anyway, we can't use trig on this because there's no hypotenuse. There's no right angle here. But anyone can make any triangle a right triangle if you try hard enough. So notice, and yes, there will be a side-side angle triangle later, SSA. You could also flip the order of those if you want. So we can have two right triangles now, right? We have a right triangle right here. Or actually, you might say this is a left triangle. And then we have a right triangle on this side as well. All right, so we have two right triangles, and we can use trig on these. So let's call this H. So we know some things, right? We can say that the sine of 15 degrees is equal to H over X, opposite over hypotenuse. All right. And we also know that the sine of 35 degrees equals H over 10. What do we have here? We have two equations. How many unknowns do we have? H and X. We have two equations, two unknown. We've got a system of equations on our hands. So there's a couple different ways of solving system of equations, but one of them is through substitution. Okay? We don't care about H. So let's solve for H and sub it out. Multiply both sides by X. You're going to get H is equal to X times the sine of 15. Multiply both sides by 10, you're going to get H is also equal to 10. It's not a 10. 10 times the sine of 35 degrees. Well, if H is equal to that and H is equal to that, these two things have to be the same. So we get the X. Lots of typos today. X times the sine of 15 degrees is equal to 10 times the sine of 35 degrees. And we could solve for X from here. I tricked you all. I tricked you all just now. You thought we were just doing a random problem. But in actuality, we just derived the law of sines. Okay, this is essentially the law of sines. So let's introduce the law of sines, and I'll show you why we just did it. Okay? So the law of sines. So let's say we have a triangle. I'm not even going to write out the word triangle. I don't have time for that. Say we have some triangle that, I don't know, looks like this or something. Where this is angle alpha, this is angle beta, this is angle gamma. Side A is opposite alpha, side B is opposite beta, and side C is opposite gamma. Getting the pattern here. Then we know a couple things about this triangle. We know that the ratio of the sine of alpha over A is the same as the ratio as the sine of beta over B, which is also the same ratio as sine of gamma over C. And you might say, Jason, that's not what we did at all. But isn't it? Right? X times the sine of 15 equals 10 times the sine of 35. We could do a little bit of algebra, right? If we divide both sides by the sine of that side, we get x over the sine of 35 degrees equals 10 over the sine, 10 over the sine of 15 degrees. And you might again say, well, that's not the same. But it is, right? Because if these fractions are equal, then their reciprocals are equal. So there's more to the law of sines. If you want to use it this way, you can. But if you want to use the law of sines upside down, be my guest. All right? You can use the law of sines upside down, right side up, sideways. Sideways is not recommended. Reversed, flip-flopped. Law of sines is very versatile. So you can see that indeed we did essentially come to the law of sines right here. X divided by the sine of its opposite angle equals 10 divided by the sine of its opposite angle. Diagonal, actually I don't think you can use it diagonally. Frontwards, backwards, upside down, those all work. Diagonally would probably be something weird. All right, so that's the law of sines. So just use any two. So just pick any two. All right, because this is like a triple equation or a double equation. We just look at this pair, maybe we look at this pair, maybe we look at this pair, or this pair, or this pair, or this pair. So many options. The law of sines is very versatile. Okay? So, the law of sines works with 3 different kinds of triangles. Okay? Let's talk about them. 3 types of triangles. All right? One of them is an angle side angle triangle. That's something like if you have a triangle where, let's say, we know this angle, we know this side, and we know this angle. This is an angle side angle triangle. It also works for angle angle side triangles. Right? Let's say we know this angle and this side. It also works for side-side angle triangles. So let's say we know this side and this angle. So it's convention to call this an SSA triangle. But the order, like you can reverse this. Well, if you reverse this, it's still ASA. If you reverse this, side angle angle, that works too. If you reverse this, angle side side, it also works. So, right, this could also be written like this. This could also be written like this. It is convention that we do not write it like this. But these triangles suck, okay? So if you want to call these ass triangles, you have my leave. I will not be calling them ass triangles, but these ones suck, okay? This case is garbage, all right? So the reason why this is angle side angle is because it has an angle and then the side between the two angles. That's why it's angle side angle, because the side that we know is between these two angles. This one is angle angle side because the side is not between the angles. It's a side on one of the sides. So I could have written this with an A here or a B here. This one's side side angle because we have two sides. We don't have the angle between them. We have an angle on one of the ends. All right. So these two are going to be really nice situations. This one won't. And any triangle that's not one of these, we cannot use the law of sines on. But we will have something called the law of cosines. Law of cosines is a messier formula, but then you don't have to worry about SSA triangles. All right, we'll get into these a little bit today. All right, so let's get solving some examples. All right, and let me know if I answered your question or not. There is no law of tangents, unfortunately, not that I'm aware of. Although, right, you could make a law of secants and a law of cosecants derived from the law of sine and cosine, right? If you wanted to, look at this. Look at this. I'm going to do this in another color so that on the notes, right? If you really wanted to be silly, isn't this the same as A cosecant alpha equals B cosecant beta? So you really could have a law of cosecants, because if you divide by sine, the same as multiplying by secants, or cosecants rather. And actually, if you had law of cosecants, you wouldn't have fractions at all, or there'd be fractions, you just wouldn't see them. So who knows? Maybe the law of cosecants is the future. If you want to use the law of cosecants on your homework, go for it. But credit me, okay? Actually, credit anonymity in the chat. All right, let's do an example. Yeah, I would love to never see fractions either, or as well. All right, so we're going to solve, well, I'm not going to tell you what kind of triangle we're going to solve. Remember, by the way, all the way to chapter 7, solving a triangle means find all the angles and all the sides. Okay? Yeah. So solve this triangle, where this is alpha, this is beta, this is gamma. All right, let's say alpha is 50 degrees. Triangle not drawn to scale. And gamma is 30 degrees. And then A is 10. So remember, we call this B. We call this C. So that the side name is just the, I don't know what it's actually called. I'm going to embarrass myself and say the English letter, not the Greek letter. There's an actual name for this. So A, alpha. B, beta, gamma. Beta, B. Gamma, C. All right. Whew. All right. So we're going to use the law of sines. But before we even use the law of sines, no, let's use the law of sines, okay? So remember, the law of sines says we can just set up any ratio, the sine of an angle divided by the side opposite it. So we need to find two things that we know and then one thing that we know. So first off, we look what side we need an angle and its opposite side. So we have to ask ourselves, okay, what angle do we know that we also know its opposite side? And the answer is, okay, 50 degrees, its opposite side is 10. So that's how we start. We say, okay, the sine of alpha, which is 50 degrees, divided by its opposite side, which is 10, is equal to the sine of something divided by its opposite side. And we just have to answer, okay, what do we put in there? Well, there's only one other angle that we know, right? Where is there? Wait. All the angles in a triangle add up to 180 degrees. So if we know two angles, we actually know the third one as well. But one thing at a time, okay? So we know that gamma is 30 degrees. So what goes in here is the side that's opposite gamma, which is C. And now we just solve this equation for C. So to solve this, we multiply both sides by C. Then they cancel on the right-hand side because it's C divided by 1. And the left-hand side, we have C times the sine of 50 degrees over 10. On the right-hand side, all that we're left with is the sine of 30 degrees. Well, now to solve for C, we just need to multiply by the reciprocal. 10 divided by the sine of 50. So we get C is the sine of 30 multiplied by the reciprocal of this coefficient. 10 over the sine of 50 degrees. All right. And it's a good idea, by the way, to get an idea of what this is. Before you type, sorry, I'm getting ahead of myself. So we need to approximate this. All right. You're going to type that into your calculator. Make sure your calculator is in degrees if you're using degrees, and use radians if your calculator is in radians. If you do this, you get, well, let's see what we get. You get 5270. And in your final answer, I'm only going to really require you to round to the nearest tenth, but it's always a good idea to add extra digits when you're calculating things. Otherwise, you get propagating rounding errors and your answer just gets less and less right. And we don't like that. We like more and more right, not less and less right. Okay, so that's C. So if you want C is 6.5, go for it. All right, so now we only need to find what beta is and what B is. But again, just like we said earlier, right, alpha plus beta plus gamma is always equal to 180 degrees. Triangles always add up to 180 degrees. Squares, parallelograms always add up to 360 degrees. Pentagons always add up to 540 degrees, I think, and then just etc. All right, well, alpha we already know is 50 degrees. Beta, well, we still need that. Gamma is 30 degrees. So we just subtract 80 degrees from both sides. We're going to get that beta is 100 degrees. Great. So now we know beta. We know alpha, beta, gamma. We know A, and we know C. All that's left is to find out what B is. So if you thought using the law of sines was fun the first time, it's even going to be more fun the second time. All right, so we get to use the law of sines again. All right, use the law of sines again. I'm abbreviating that because I don't want to write law of sines every time. So we do exactly what we did the first time. Every time you're using law of sines, the first part of the equation is sine of an angle that you know divided by a side you know. Right, and now we know what C is now, so we could have used that as well. Choosing this one is better though, because this is an exact answer. If we chose sine of 30 degrees divided by C, which is 6.527 whatever, then we have an approximated answer. And having an approximated final answer is fine, but if you're approximating with your calculations, then your second approximation is going to be an approximation of an approximation. It's like taking a copy of a copy, and it just gets worse. Am I going to mark points off? No. But if your error gets really, really bad, I will certainly at least raise an eyebrow. Okay, so we're going to have the left-hand side for our law of sines be the same as before. Sine of 50 degrees over 10 equals the sine of an angle divided by the side. And remember, we want B, so we need to take the sine of 100 degrees divided by B. And again, we solve this the exact same way we solved it before. Multiply both sides by B, multiply by the reciprocal. We don't need to do the steps again. You know how to solve equations like this by now. And you're going to get that B is equal to the sine of 100 degrees times 10 divided by the sine of 50 degrees, which we will also approximate. All right. And what you're going to get is sine of 50 degrees. So, nope, that's not it. Sine of 100 degrees times 10 divided by the sine of 50 degrees is going to be about 12.8558 approximately. So we just fill that in. That's about 12.9. Now, we have solved the triangle. We know everything about this triangle. Here's the time for a gut check. Okay? I'm going to write this here so that we can have it side by side. Note, the bigger the angle, the bigger its opposite side is. So what that means, what's our biggest angle here? The biggest angle in this triangle is 100 degrees. Its opposite side very darn well better be the biggest side. Biggest angle means the opposite, it's got to be the biggest side, okay? So you can use this to check your answer. It's not a foolproof check, but it can catch a lot of mistakes, okay? Biggest side, biggest angle, good. What's the smallest angle? Smallest angle is 30 degrees. Its opposite side should also be the smallest side. And it is, 6.5 is the smallest side, okay? So just a little gut check a little way to make sure that you didn't make a huge mistake. All right. We're going to be trying to do that with every single one of these problems. All right. So let's get into side-side angle triangles. These are the really interesting ones, the ones that are really complicated. After we've done a couple of these, problems like example 1 are going to be pretty straightforward to you. Example 2 is really where things get a little tricky. Because if you have a side-side angle, or again, if you want to call it something else, you can call it something else. You have a side-side angle triangle that has 3 cases. The book says 4 cases, but I really think it's only 3 cases. All right. Sometimes when you're solving these cases, you get a broken case. It doesn't reach. Sometimes you get something like, oops, not beta. If you know an angle and then a side and then another side, sometimes you're going to get a broken triangle. Sometimes you're going to get that there's no solution. We'll see what that looks like. Sometimes, all right, this sort of happens when A is not big enough. If A is too small, it can't reach this bottom side. So it just kind of dangles here, and there's no triangle. It doesn't reach. Sometimes A is too long. If A is too long, what you sort of get is you get 2 triangles. Maybe the side swings that way or the side swings this way, and you just don't know. Right? And we'll show what this looks like as well. One of these will be an obtuse triangle because there's an angle bigger than 90 degrees. And the other triangle will be an acute triangle because they're all less than 90 degrees. Sometimes you might get 2 solutions. These situations kind of suck. And sometimes maybe everything's going to behave. Sometimes you're only going to get 1 solution. And that makes us happy. Honestly, getting the no solution is kind of a happy situation as well. Because really quickly, you find out that there's no answer and you're just done, right? It's like you're halfway through a problem and you say, oh, there's no answer. You just don't have to finish the problem. You just say there's no answer. This one is also a pretty good solution. 2 solutions, though. This is really the one it's not that great. All right. So we'll cover that. We'll cover all these cases with example 2. All right. So the important thing is that you can recognize which situation you're in. That's what we're going to finish the video with today. Let's do example 2A. We'll save the rest of the examples for tomorrow. All right. Yeah, I'm getting better at drawing angry faces. My 1400 class, they give me a hard time if I draw bad faces. All right, so let's do example 2. Solve. I'm just looking at my notes right now. We'll cover that next time. Sort of skipped something. All right, so solve the following triangles. Part A. It's, let's solve a triangle where alpha is equal to that's 35 degrees. B is equal to 8, and A is equal to 6. So sometimes you won't be given pictures. And most of the time on quizzes and exams, I won't give you pictures either. So we don't know what it's going to look like. We have to draw a picture. So just draw some random triangle. It does not matter what your triangle looks like, because if you knew what the triangle looked like, you wouldn't be solving the problem. So just draw some random triangle. It's not going to look anything like the numbers that you plug into it. So just keep that in mind. And again, this will be alpha, beta, gamma. Alpha is 35 degrees, so fill that in. B is the side opposite beta, so that's going to be 8. A is the side opposite alpha, so that's going to be 6. Actually, the triangle looks pretty good so far. All right, so let's use the law of sines. Remember, to start the law of sines, we need to find an angle and an opposite side that we both know. So we know this angle and its opposite side, so we start with this. The sine of 35 degrees divided by its opposite side, 6. And now we find either an angle or its opposite side that we know. We need to know one of these things. The only other thing we know is B. So we're going to put in B here, which means beta has to go in here. So we're going to have to solve for beta. In the other situation, we knew the angle, so we had to find the sides. Here, we know the sides, and we need to find the angle. So let's see what happens. Let's see which one of these cases we're going to get. Are we going to get happy face, angry face, or other happy face, but not quite as happy? Let's see. So to solve for beta, we multiply both sides by 8 to get that sine of beta equals 8 times the sine of 35 degrees divided by 6. And what have we got here? We've got ourselves a trigonometric equation. We just did that. That was the last section, 9.5. 9.5, the whole thing, we talked about solving trigonometric equations. And remember, we said trigonometric equations oftentimes have infinitely many solutions. So that's where this two-solution case is going to come into play, because there will be two angles in our domain that make sense. The no solution, we'll see what that looks like as well. So let's just see what situation we have. Let's approximate this right-hand side. Let's see what we're dealing with. 8 times the sine of 35 degrees divided by 6. What number does that look like? That number is approximately 0.7648. Okay, so we're going to at least have one solution. If this right-hand side was like 27, sine of beta is never going to equal 27, right? So we'd be in a bad place. So let's see what we've got here. Okay, so sine of beta is equal to this approximation. So to find beta, we need to use the inverse sine. And remember, inverse sine only gives you one answer because we restrict the domain. There might be multiple. So let's see what beta is equal to. Beta is going to be equal to the inverse sine of all this. If you want the best approximation, you type this whole thing on the inside of the inverse sine. But if you just want to do this, that's okay as well. Just make sure you use at least 4 decimals. All right. And again, you type this into your calculator, making sure that you're using degrees. We're doing degrees for like all of this. All right. So inverse sine of 0.7648. You're going to get 49.8892 degrees. But that's only one answer, right? We talked in the previous section that there are infinitely many answers to trigonometric equations. This is one answer. What other quadrant? This is the answer in the first quadrant, right? But there's also an answer in the second quadrant, because sine is also positive in the second quadrant. So we need to find the supplementary angle here, right? A reference angle of about 50 degrees in the first quadrant. That's one answer. But also there's also that reference angle of 50 degrees in the second quadrant, and we need to find that whole thing. So we're going to take 180 degrees minus that 50 degrees. Okay. We're going to call that B prime. It's starting to look like we're going to have two answers here. Right? It's going to be approximately equal to 180 degrees minus that 49.8892. What's that equal to? I'm not doing that in my head. Dang it. Sorry. 49.8892. That's going to be 130.1108 degrees. Is this possible? Well, yeah, it's possible. So we can have two answers here. So this is where the problems get really sticky. We got the angry case. We found one triangle with a beta of this, but we found another triangle with a beta of this. We got two triangles. All right, so strap yourselves in. This problem just went double or nothing. But not double or nothing. It just went double. Okay? That means that tomorrow's lecture will be a little nicer. We'll get nicer cases tomorrow. So again, before we move on, I just really want to recap what's going on here. We know, let's cover this up and pretend it doesn't exist. We know that the sine of beta is equal to this ratio, this answer. But there are two solutions to this equation that make sense. Remember in 9.5, we said there's infinitely many solutions to trigonometric equations. Most trigonometric equations. So there's two answers that make sense here. So we found the reference angle and we said, okay, that's the reference angle that makes sense, just like we did in the previous section. And then there's two answers in terms of triangles that make sense. The reference angle in the first quadrant and the reference angle in the second quadrant. So that's why we got a second angle here that we're just calling beta prime. Okay, because there's two possible answers to this. Two possible answers. So this is really 9.5 where this confusion kind of comes into play. All right, so really, this is a really bad time to turn the page. But we got to do it, okay? So I'm going to turn the page, and I'm just going to rewrite what we already know so that we can reference it. So we have two triangles. All right, one kind of looks like this, maybe a little bit more obtuse, right? Maybe like this, alpha, beta, gamma. Wait, this is what we're calling beta prime. And then we also have an acute triangle, which maybe looks like this. All right. This is our original triangle, alpha, beta, gamma. So alpha and alpha prime are both they're 35 degrees in both triangles. That was given to us, right? What else was given to us is A was 6 and B was 8 in both triangles. This is 6 and this is 8 in both triangles. This is 6, this is 8 in both triangles. But we said that beta is about 49.9 and alpha is about 130.1. 49.9 degrees is beta, and I said that wrong. Beta prime was about 130.1. We got two triangles here, one with an obtuse angle and one with an acute angle. So of course now we really have two problems. Right? Here's the prime triangle. We'll solve it on that one. And the non-prime triangle. We'll solve it on this side. So one problem became two. We're going to solve both triangles. We'll solve with the non-prime triangle, this one. We don't have to write primes everywhere. We know alpha, we know beta, so we immediately know gamma, right? 35 degrees plus 49.9 degrees plus gamma has to equal 180 degrees. The sum of all the angles of a triangle has to be 180. All right, so you just solve that. Again, I don't need to do all the steps. You know how to solve equations like this. And you're going to get gamma is 180 minus 35 minus 49.9, which is 95.1 degrees. So fill that in. 95.1 degrees. Great. And now the only thing missing in this triangle is the value for C. Well, let's see, how do we find a side, given that we know information about angles in the other side? Let's use the law of sines. All right. Yeah, you tell me what 95.1 is, the radio station. Maybe we'll play the music as we solve it. Actually, I'm not going to play any music. That's just what I need as a copyright infringement on my math lecture. That's funny though. So let's find C. We still need C. Okay. So we just pick an angle and an opposite side. And again, it's usually best to use the ones that aren't approximations wherever possible. So just like before, sine of 35 degrees divided by its opposite side, 6, is equal to the sine of something divided by its opposite side. And remember, what are we trying to find? We're trying to find C. KYCS is really an unfortunate acronym. And maybe I play too many online video games, but When I see this, I don't see the C. And in online video games, this is not a nice thing to say. Let's go ahead and remove that from my notes. All right, so we need to find C. What's the opposite angle to C? Gamma, which is 95.1. KYCS. All right. And you just solve this. Okay. Again, you know how to solve these. Multiply both sides by C and then multiply by the reciprocal. I'm not going to waste time doing those steps. You're going to get that C is equal to the sine of 95.1 degrees times the reciprocal 6 divided by the sine of 35 degrees. Yeah, I have never listened to our Mustang radio, but hopefully it's awesome. So you just type this into a calculator and get an approximation. The sine of 95.1 degrees. If I can type things in correctly, times 6 divided by the sine of 35 degrees. You're going to get about 10.4193, or again, you really only need one decimal point here, so 10.4. We have solved the triangle. We haven't answered the question. We haven't finished the question, but we have solved the triangle. We know all the sides and all the angles for one of our possible triangles, but we have two. So now we need to go right over here and do it again. All right, you see why I wrote the angry face for these. And you can also see, right, why SSA triangles, or alternatively ASS triangles, kind of suck. All right, they're not the ideal case. So let's do it again. So we find gamma prime the same way that we found gamma. We have two. As soon as you get two angles, you're on easy street. You find the third, no problem. 35 degrees plus 130.1 degrees plus gamma has to equal 180 degrees. So you just subtract those things over. And you're going to get gamma equals, I can do this in my head, right? Let's not do this in my head. You're going to get 180 minus 35 minus 130.1, which is 14.9. Okay? It's approximately equal to 14.9. I think that's what I said. Yeah, these homework assignments are long for sure. 9.5 and 10.1 are pretty long homework assignments. But these SSA triangles don't always end so poorly. But yeah, it is a long assignment. Intentionally so. I don't know if I've spoken about that in this class, but I do intentionally make really long homework assignments because the only way to really learn math, you can't just watch a video and go, oh, I'll remember that, no problem. I understand it, no problem. You really have to just kind of use this as a springboard to actually learn the material by just doing a whole bunch of problems and seeing like what happens and how to do it, which is a time sink. So it really sucks, but that's kind of the only way to really do math. All right, so we now have gamma prime. And again, well, just like we did over here for this triangle, we found gamma, we needed C. Well, we found gamma prime, and now we need to find C prime. Okay, so just like before, we can use the same thing. Sine of 35 degrees divided by its opposite side is equal to the sine of gamma prime divided by its opposite side, C prime. And again, you just solve this the same way you solved it before. You can get C prime is equal to the sine of 14.9 degrees times 6 over the sine of 35 degrees. Type that into your calculator. You get an approximate answer. And what do you get? 14.9. You're going to get about 2.6898, or about 2.7 for C. So what did we do at the end of last example? At the end of example 1, we said, let's do a gut check. The biggest angle should have the biggest side. Let's look at the biggest angle. The biggest angle in this triangle is 130 big degrees, and its opposite side is 8. All right, good. 8's the biggest side. This is good. What's the smallest angle here? 14.9 degrees. Is its opposite side the smallest? Yep. Good. So our little gut check works out on this triangle. Let's take it over to this triangle. Biggest angle, 95.1 degrees. Opposite side is 10.4. That's the biggest side. Good. Smallest side is 35 degrees. Opposite side is 6. Yep, that's the smallest side. Good. That's good. That's real good. All right. And this video turned out longer, but I'm glad I got to take my time solving these example problems. This problem, example 2A, is difficult, okay? As you come across these in the homework, feel free to contact me via email if you have questions or if you just don't know how to start, all right? But the reason why there's two triangles is when you're solving the triangle, remember there's infinitely many solutions. So we take the two solutions that make sense in the context of triangles, right? Because another solution to this equation right here would be this angle plus 360 degrees. But we're not going to have a 400-degree angle in a triangle. That doesn't make sense. So we usually only look at the first and second quadrants for these law of sines. All right? Anyway, we'll be back again tomorrow. We'll finish up the section. And again, we're only having 2 online classes a week now, just so we can kind of let the face-to-face class catch up, and I can kind of do them both at the same time. It doesn't really make sense to do them both separately. All right, so let me know if you have questions, and enjoy the homework. Oh, you have an exam this week, remember. The exam will cover 9.2 up to 10.1, all right? And that is already published on Canvas, and it will be due next week, Thursday. As of the recording of this video, you can see all the dates in Canvas yourself, depending on when you watch the video. Anyway, have a good day. Okay, so that's it for the lecture.